Hello, am I audible? हेलो, मेरी आवाज आ रही है क्या?
Yes, sir.
ओके प्रियांशु। अच्छा, आप लोगों में से कितने लोग क्रेडिट कर रहे हैं कोर्स को? हाँ, कि वो क्रेडिटर्स अपने हैंड रेस कर ले। बस 5 ही आए हैं क्रेडिटर्स क्या? टाइम भी सेट करना था, 5 तो कम है। और कोई है क्रेडिटर या बाकी सारे ऑडिटर्स हैं? ओके, चिन्मय पाटिल भी क्रेडिटर है, ठीक है। ओके, थोड़ी देर और वेट करते हैं, मे बी और ज्वाइन कर ले। क्योंकि अगर एटलीस्ट कुछ इनफ नहीं हो तो फिर फायदा नहीं है डिसाइड करने का क्लास टाइम।
So can you repeat what you just said? Computer audio.
Yeah, Aditya, you were not. One second. Can you repeat that?
So I couldn't hear properly because my audio was not working properly.
Oh, okay. So what I'm saying is, I wanted to know that how many creditors have joined, because we also need to discuss the class timings. So, but how many creditors have joined basically? But only 5 or 6 have joined till now. So I will wait for a bit of time, so that we have enough creditors so that no one gets left behind.
Okay, sir.
How many total creditors are there, sir?
As per my knowledge, around 10 to 12 people wrote in the form that they are creditors, the form that I floated on the Moodle. So I'm at least waiting for like 7 or 8 because to cover the spread.
Okay.
Okay, you may put your hands down for now. We will just visit the discussion for timing a bit later on in the class. Okay, so this time I'm going to try something completely different. So usually when we used to do these classes, what we used to have a code and we used to just go through the code lines one by one. But this time I'm not going to do that. I'm going to try something completely different where we are going to actually write the codes and I will explain line by line that what is exactly I'm writing. I might copy paste some lines because they are pretty much common lines and but yeah, I will explain that why I'm writing this line and everything. So this is the first time I'm trying this. I thought that this will be really more helpful. Moreover, how many of you have worked with Python before? Raise your hands. Gitanjali and Dipti, you have not worked with Python before?
Yes, sir. Yes, sir.
Okay. You are Gita. Okay. Dipti, have you not worked with Python before? Okay, maybe not here. Okay, so I'm assuming majority of you have worked with Python, so I won't go into detailed working of Pythons. Okay. How many of you have worked with TensorFlow or Keras? Basically, work with is that you have created a sequential model using model.compile, model.fit, that kind of work. Okay, so raise your hands. Those people who have worked with TensorFlow or Keras, they know what is model.sequential, model.compile, model.fit. Who have that much of knowledge. Okay, so Aditya B1, B18028. What's your name?
Sir, Swapnil.
Swapnil. Okay. Swapnil, Dharam. Okay, so many people have not worked with TensorFlow Keras. Okay, good. See, the point is sequential API is very simple. If you go to TensorFlow's tutorials, you can easily understand that. It's a very simple API and it's actually pretty much useless API. Uh, uh, okay, so we are not going to cover that. We are going to actually understand what's happening behind the scenes. We are not going to use model sequential, whereas we are going to create our own custom models. We are not going to use model.compile. We are going to define our own gradient optimization. We are not going to create model.fit. We are going to create our own training loops. Okay, so how many of you know that how a deep learning model is trained? The theory part of it, not the practical part. Very few people. Okay, hands are coming up. Okay, so I want to repeat, please raise your hand if you know the theory of how the deep learning models are trained and keep your hands up. Chinmay, do you know about the basics of DL? You know, Gahan also knows. Utkarsh Kaushik, do you know the basics of DL? Yeah, I mean, see, yeah, Priyanshu, that's a good question about Pytorch versus TensorFlow. See, the basic aspects of both are very much similar. Just the functions change, but how they are working, they are very much similar. The, we will cover a PyTorch lecture as well. Ranjit sir will take it. If a lot of students want to cover things in PyTorch, Ranjit sir can take it. He's better suited to cover PyTorch. Whereas most recent papers, I agree, are on PyTorch, but you can still do all of the things that you need to do in TensorFlow. And a few of the recent papers are in TensorFlow as well. And my core working is in TensorFlow, and basically, and to the level that what's happening inside, where I can create my custom models, my custom layers, my custom optimizers as well inside TensorFlow. Of course, I won't be going into details of everything, but I will want to give a proper expert view of TensorFlow. I don't want to just go with sequential modeling. And the way I will tell this TensorFlow system, in Python, the things are 99% similar, just the functions change and some strategies changes, but the things are 99% similar. And I can ask Ranjit sir to give a lecture on PyTorch later within the period. Okay. Hmm. Okay, fine. So just to recap, I mean, okay, so who? Priyanshu. Yeah. Can you unmute yourself?
Yes, sir.
Yeah, Priyanshu. Okay. So what are the steps while training a network? What happens when we want to train a neural network?
So we have some training data. We
Yeah.
first pass it through the model and get some predictions over it. Then we
Okay.
compare those predictions with the actual predictions and cover it with some loss function so that we can quantify it. Then
Okay.
we do the gradient descent algorithm on the loss so as to reduce the loss and train the model parameters in that fashion.
Cool. Yeah, that's perfect answer that I was looking for. So I will just now reiterate what he said. I'm going to share my screen. Okay. Wait. Which screen is visible? So what can you say in the screen? I'm having two screens and I'm not sure which one is visible.
An introduction to artificial neural networks. The
Yeah,
one
the
with break.
figure, right? The one
Yeah.
with figure.
Yeah.
Got it. Yeah. Okay. Yeah. So okay. So what we are having is we are having a neural network. Neural network contains input layers and output layers and hidden layers. Now, how the input layer is defined? Input layer is defined uh, by the properties of your input. Okay. So let's say now currently we will talk about fully connected networks. We won't go to convolutional networks. So in fully connected networks, if I want to create an image classifier, fire. So the number of pixels in the image will be my shape of my input layer. So let's say that I'm working on MNIST dataset. In MNIST dataset, my images are one sec. I'm not sure. 28 cross 28. Okay. So some 764, I think, is the value of 28 into 28. So my input layer will be 764. Now, how do you define your output layer? Output layer is defined by the task that you want to perform. Okay. Let's say that on MNIST data, I am performing a task of classification. And what classification? I'm performing the task of classifying digits. So there are 10 digits from 0 to 9. So it's a 10 class classification problem of classifying digits because we have 10 digits. So if it's a 10 class classification problem, the output layer will actually have 10 neurons. So the input and output layers, how many neurons input and output layers have, that is dependent upon the type of data we are having and the task that we are performing. Let's change it a bit. Let's say the task I'm performing is localization, object localization. And I know for a fact that there is only one object per image. So to localize any object, I need to create a bounding box over any object. Okay. So for creating any bounding box, I need four values. What are the four values that I need is that I need the coordinates of the center of the box and I need the width and height of the box. So the coordinates of the center will be x coordinate and y coordinate. So two values there. And then I will need width and height of the box. So basically I will be needing four values to create localization issue. So in that case, the output layer will actually have 4 neurons, where the first neuron can give me the center X value. The second neuron will give me the center Y. The third neuron will give me the width of the box, and fourth neuron will give me the height of the box. So the output layer is dependent upon the task that we are performing, and the input layer is dependent upon what is the input that we are having. So if it's eminist video, this will be a 764 neurons. If we are working with images that are say let's say 224 cross 224, so in that case the input size will be very huge. And then we have hidden layers. We can have it's up to us to define how many hidden layers we want. uh, Usually what we prefer to uh, create we prefer to have a tall model rather than a fat model. So what I want to say is basically this is a fat model. If we assume that we only have one hidden layer and the number of neurons in hidden layer are greater than input and output, then this is basically a fat model. Whereas we prefer sort of like tall model, where the number of neurons in hidden layer are usually less than the input, but we have multiple such hidden layers. We prefer a tall model rather than a fat and short model. So, and how we train a model. So we have an input. Okay. Now each of these arrows, they actually have some weights, which is that the weight gets multiplied by the value of the previous neuron or the value of the input. And here we apply on every neuron, we actually apply yeah. Uh, Hello, Balkar.
नहीं सर वो गलती से नहीं कौन रहेगा
Okay, yeah, no problem. Yeah, so what I was saying is that so basically the pixel values will be at the input. At each of the arrows, we have the value of the weights. These weights are multiplied by the input, and then all of the arrows, the output of the multiplication is added. And then here we apply any nonlinear function. It can be a sigmoid, it can be a ReLU, which applies that function over the additive output, and finally we get the output of a neuron. And similarly, again, that output of a neuron acts as the input for the next neuron, which is again multiplied with the next weight value, and this thing keeps on repeating for the complete till we get to the last layer. Now for any given input, we first do a forward pass, in which initially we can have some weights. Those weights can be wrong, those weights can be right, we don't know. No, but one thing is sure, if those weights are wrong, we need to get them to the right position. Okay, so we get an input, we pass it to the network, we keep on multiplying with the weights and adding and applying activation, multiplying with the weights, adding and applying activation at each of the layers till we get the outputs from the output layer. So once we have got the output from the output layer, we compute the loss. So for computing the loss, we have some ground truth with our case. The ground truth is the output which was supposed to come for this input. So if we have the ground truth and if we have the output that actually came from the network, we compute the loss between those two. Now this is my forward pass. Up till the computation of loss, this is called a forward pass. Now once this loss is computed, we use the chain rule to compute the gradients of each of the weight values with respect to the loss. So for that, we actually utilize the chain rule to so that we initially compute the weight values of the penultimate layer, then we go one layer back, then we go one layer back till the time we actually get to the first layer that we were having, and we utilize chain rule for computing the gradient of the weight with respect to the loss. Once we have computed the gradients, we update the weights using those gradients utilizing some optimization framework. Now, a very simple optimization is just weights minus neta times gradient. So you just have a gradient. Okay, you multiply the gradient with the learning rate, that is my neta, and then you just subtract w from with my neta times gradient. So this is the simple gradient descent. However, this is not useful at all. This has a lot of problems, which you can actually see on your own. We actually have some complex optimizers. Now, another thing, all of these complex optimizers are gradient descent based, but they just do not use a subtractive way to update the weights. They are all gradient descent based, but they apply some tips and tricks so that the weights update is as smooth and as good as possible. And once the weight is updated, the whole cycle, that is the backward pass, is complete. So the backward pass consists of two things, that is the computation of gradients and the update of the gradients. So the forward pass contains two things, that is computation of the output and computation of the loss, and backward pass contains two things, that is computation of the gradients and updating the weights with respect to gradients. So these are the four aspects that that happen on training a neural network. Hope this is clear to everyone. There's no issues here.
Sir, I have a doubt.
Yeah.
So what's the logic behind not using more number of neurons in hidden layer than the input layer? Like you
Okay.
said,
So
there's
so logic behind this. So let's say that I am working with an input size of with an image. Okay. So what is the usual size of the images that you see in real life, that you see on your computer, that you see on your phone? No, I want that output from you. I want the conversation to happen from you as well. I just don't want it to be a monocolor lecture. Hello.
Sir,
depends. I mean, which picture we are talking about.
In general, if you click a photo from your mobile, or you just usually see any photos, what is the usual size of images that you prefer to watch?
Size of the screen.
Size of the screen. I mean, we won't go into 4Ks, but HD images at least. At least HD images, right? And what is the size of an HD image? Can anyone tell me? A high definition image.
Ten eighty into 960, something like that.
1080, 960, it can be 1080, 720, depending upon them. Yeah, basically, assume, let's say 1080. So in x-axis, we have 1080 pixels, and if we can go for 1080 into 720, we can have a widescreen monitor. So which is 1080 into 760, I think. Okay. So what is the size of the input layer for a 1080 into 760? So so what we do is, our image is 1080 pixels in x-axis, 780 pixels in y-axis. So if I flatten it, what will be the size? The size will be 1080 into 760. Oh wait, I'm on Brave. Sorry for that. Yeah, 1080 into 760. So we have basically 8. Yeah, almost a million number of pixels. So 800,000 pixels, almost a million number of pixels. Okay. Now your initial input layer has million pixels, almost a million pixels. If you create your hidden layer, which is, let's say, more than this, where the number of neurons is actually more than this. So what will be your, so let's say I create another hidden layer of a million pixels. What do you think the number of weights will be in that first layer itself?
Considering fully collected.
Yeah, fully connected. So the input is a million neurons. The hidden layer is million neurons. So how many weights are going to be there?
Million layers cross million.
Yeah, million cross million. Okay. So that's a trillion weights in just a single layer, and that will never work. Okay, and this was an extreme case that we are working with HD. Let's not just work with HD. Let's work with images. We downsample the images. Let's say 224. Okay. So now I'm having an image which is 224 cross 224, which we usually see. So even in that, the first neuron will have sometimes like 50,000 neurons. And let's say I create a layer of 50,000, sorry, into 50,000. We are actually getting 250 million neurons in just a single layer itself. So having a hidden layer that is greater than or even equal to the input layer, that the one issue is that the number of parameters, they increase exponentially because there's a multiplication involved. Second issue is, let's talk about any image. Okay, let me just take any face image. The internet is slow. And the internet is a bit slow. Okay, so let me talk about this image. Okay, now the classification that the problem that you want to solve is that who is this person in this image? Let's say that is the problem you want to solve, and you have this image with you. Okay, so the total number of pixels are going to be very huge. Let's say even if you downscale this image to 224 cross 224, the total number of pixels are going to be around 5,000. But are any of these pixels important for your task? Any of these pixels?
No, sir.
No. Any of these pixels are important for your task? No.
No.
Any of these pixels are important for your task?
Yes, because we need to know how much head size is there.
Ah, but not all the pixels are important, right? You can just know
Yeah.
the head size from knowing this pixel and this pixel. You don't know all, you need not to know all the pixels in between. So basically, if I tell you that you need to create your own system for face recognition, what you will do, you will actually select some key points in the face, and you will say that if these key points in the face, they match with in two different images, then that person is the same person. And those key points will be very limited. These can be 2400, even you might create 500 key points, but that's it. You don't need more than 500 information values to know that who the person is. So that's why we always have lower amounts of neurons, because we do not, because majority of the information in the input is redundant and not necessary at all. We actually need a very small amount of information that we need to extract from our face. So that's why that information can be extracted very efficiently by having a less number of neurons in the hidden layer. But the problem can be that the classification boundary can be very, very, very complex, what I want to achieve. So that's why we prefer to have more and more hidden layers, because each hidden layer will introduce more and more non-linearity. And as I can introduce more and more non-linearity, I can actually create a system which can classify for very much non-linear decision boundaries. So that's why we prefer to have more and more layers, so that we can create very huge non-linear decision boundaries. But since only a very small amount of information is important for us, we can have less number of neurons in every layer. And this is true for any kind of signal, any kind of input, because every data is redundant. Majority of the data is redundant. I hope this clarifies the doubt.
Yes, sir.
Okay. Okay, so I think many of the students have joined. Okay, so Priyanshu, can you just put your hand down for a minute?
Sir, another small thing in this topic called tall over fat is, I just want to confirm once. Hello?
Yeah, I'm listening.
Yes, yes, sir. Yes. In a use case, I just saw there is a problem of vanishing gradient. If we have a tall network, I mean, the more the layers, we might also
Okay.
face that problem also. So they suggested to use the skip connections.
Yeah, that's correct.
Are these the trade-off on choosing the model as per our requirement, or?
Okay, so basically I will come to that later on,
Okay, sir. Okay.
Dharma. Okay, I don't want to
Yes.
get into that. So for tall models, I'm not talking about models of 50, 120, 150 layers. I'm talking models of 10 layers, 15 layers, 16 layers. So vanishing gradient problem won't occur right now. But
Okay, sir.
I'm talking about tall model. Okay, but however, those issues, so basically Dharma, so those issues we won't be covering because they are deep learning based, but those issues have been discussed in depth in sir's lectures.
Yes, sir. But just to confirm, I just asked. Okay, sir.
Yeah, so if you have a model that's having, let's say, more than 20, 25 layers, you need to have skip connections.
Yes, sir. Okay, sir.
Okay, so now I want everyone to raise their hands who have credited the course. Okay, yeah, that's a good number. Okay, so so what we are going to do is we're going to try to set 2 slots of 1.5 hours each. Okay, in second half or a bit later in the evening. So what are the days that Aditya sir is free? They are except basically Monday, Tuesday, Wednesday, Thursday, Friday. Sorry, not Monday, Tuesday, Wednesday, Thursday, Friday. So 4 weeks, 4 days are there available with us. Okay, so on Tuesday, is anyone busy from 2 to 3:30? You can unmute yourself and speak.
Sir, I think we have POP lab.
Okay, 2 to 3:30. Okay. When does it get over on Tuesday?
Wednesday, yeah, it's free.
No,
Wednesday,
Sir, on Tuesday it is from 2 to 5, the lab.
Okay, it is from 2 to 5. Okay, so let's Tuesday. Wednesday, anyone is having anything between 2 to 5 in that period?
Me, sir.
Uh,
I'll have physics practicum.
okay, from 2 to 5, Wednesday.
Yes, sir. Yes, sir.
Okay. Thursday 2 to 5, is there anything?
So Thursday 2 to 5, I have my physics practicum slot.
I also have
Okay.
physics practice.
And Friday 2 to 5?
Sir, computer organization.
Complete 2 to 5 or 2 to 3 or something like that?
3 to 5.
3 to 5. Okay. So what about Friday 1 to 2:30? Anyone has any class from Friday 1 to 2:30? Okay, so I'm assuming that no one has. So one slot, what we can, I will confirm the slots with sir. One slot that we are having is,
सर
I will
हाँ
just,
वन थिंग जिनका वो फिजिक्स प्रैक्टिकम है, क्या वो मतलब एक दिन में मतलब सबका स्लॉट नहीं हो सकता है क्या, अगर मतलब प्रोफेसर से बात करें तो?
एक्चुअली हमारे कुछ लोगों के सेकेंड ईयर से फिजिक्स प्रैक्टिकम्स रहते हैं जब कोविड शुरू हो गया था, एंड कुछ हम इलेक्ट्रिकल वालों ने मेजरली फोर्थ ईयर में अब जाके लिया है, तो बहुत सारे बच्चे हैं. आई डोंट थिंक एक दिन में वो कर सकते हैं.
नहीं मतलब सिर्फ एक
शायद
स्टूडेंट का ओनली,
आई
मतलब
थिंक ही इज ट्राइंग टू
या
से
तो
कि
आपका उनके साथ हो जाए या
हाँ,
एक टाइम.
मतलब जो लोग ये कोर्स ले रहे हैं उन सबका एक दिन हो जाए, मतलब ऐसा।
हाँ
मेरा और चिन्मय का तो सेम डे है, तो बाकी कोई मतलब हमारे साथ कर सकता तो देख लो, किसी का एक बंदे का या कर दो किसी और दिन।
आई डोंट नो फ्राइडे और किसी का है क्या अभी इस क्लास में? आई गेस नहीं है। अगर नहीं है तो मैं एक बार सर से बात कर लूंगी, इफ दैट्स पॉसिबल। मैं थर्सडे या पिछले वाले स्लॉट में करा के देख लूंगी।
या थैंक यू दीप्ति, एक बार सर से बात करके बता देना, ठीक है?
यस सर।
ओके, सो मतलब बेसिकली फ्राइडे को छोड़ के मतलब 2 to 5 तो किसी भी दिन अवेलेबल नहीं है, ठीक है? लैब वो चलते हैं। ओके, ट्यूसडे 5 to 6:30।
सर चलेगा मेरे को तो। आई डोंट नो अबाउट अदर्स।
नहीं वही तो बात है ना, हर कोई बोलेगा चलेगा, वो नहीं, मेरे को बस वो चाहिए कि जिसको एक्चुअली वहां पे कोई प्रॉब्लम है। अच्छा ये बताओ, हर डे पे 5 to 6:30 किसी डे पे किसी का कुछ है?
नो सर हमारा
नो सर।
सर 5 बजे के बाद में किसी का कुछ नहीं है शायद।
5 बजे के बाद किसी का कुछ नहीं है ना, ठीक है।
नहीं सर।
और ओके गॉट इट, सो मेरे को एक आइडिया मिल गया, गॉट इट। और दीप्ति, कैन यू जस्ट यू हैव माय कांटेक्ट इंफॉर्मेशन?
सर आई थिंक आई हैव इट।
Okay, so try to contact me if you get any information, positive or negative. Okay.
ओके सर, मैं सर से एक्चुअली शाम तक बात कर लूंगी।
ठीक है, so yeah, I got an idea. So basically 5 to 6:30 everyone is free and every day, but 2 to 5 सिर्फ Friday को अगर हो सकता है, so okay fine, I will talk to Aditya sir then to finalize, and final time will be uploaded on Moodle. Moodle, I will also send a mail to everyone, but and another thing, many information will keep on uploading on Moodle. Please make a habit of just logging into Moodle and checking every day. Okay, just create that habit.
So you're trying to keep one lecture after 5 or both the lectures after 5?
Let's try. So ideally we don't want to keep both the lectures after 5.
Yes sir.
Okay. So what we will try, see, even 1 to 2 is a bit frowned upon because that is lunchtime. We don't want to keep it between 1 to 2:30 as well. Okay. So we want to see if on Friday we can get the 2 to 5 slot. If we don't, then I will talk to sir to keep one on any 1 to 2:30 and one on 5 to 6:30.
I think we can have it from 1 to 2 because the lunchtime is actually from 12 to 1. We have actually other lectures from 1 to 2. Some on other days.
Yeah, okay. Yeah, I understand that part. Okay. Okay, so from 1 to 2, there's no, the lunchtime this time is from 12 to 1.
yes sir, according to timetable lunch time is 12 to
Okay.
1.
Okay. Yeah, then that's fine. Friday 1. So Friday 1 to 2. So Friday from 1 to 2:30, nobody has a problem, right?
Sir, I might have a course. I'm not sure if I'm taking it, but it's not 100% sure, but I might have it. So I don't know.
Okay, Thursday 1 to 2:30.
Sir, I have a lecture from 1 to 2 Thursday.
Okay. Wednesday 1 to 2, anyone has a lecture?
Yes, sir.
And Tuesday?
So Tuesday is actually ADL from 1 to 2. Like this course only.
Okay, so the Tuesday lab, the people who were saying Tuesday lab, is it from 2 or 3?
Sir 2. 2.
Tuesday lab is from 2. So from 1 to 2:30 as well, no slot is free. Uh, Okay, so who said about Friday 1 to 2:30? They're not sure.
Sir, I will confirm it to you as well.
Yes. Okay,
Yeah.
so for Friday, please confirm me both of you about 1 to 2:30, 1 to 2 and 2 to 5. Okay.
Okay.
Otherwise, then there is nothing else. Okay. What about let's say 10 to 12? 10 to 12 on Tuesdays. Anyone has any classes?
Yes,
Yes,
sir.
sir.
Okay, Wednesday.
Yes, sir.
Thursday.
Yes, sir. Yeah.
Okay, and Friday.
Yes, sir.
Ah, okay, Monday.
Yes, sir.
Okay, so let's see. This is uh
तो ये ए स्लॉट में नहीं हो सकता क्या, अगर किसी का भी अगर ए स्लॉट में नहीं है तो
hmm?
ये कोर्स ए स्लॉट में नहीं हो सकता क्या, मतलब अगर किसी का भी ए स्लॉट के साथ कुछ क्लैश नहीं हो रहा तो
किसका
like,
है ए स्लॉट? किसी का ए स्लॉट है?
हाँ सर मेरा है।
Yes, sir. I
हो
have.
हो गया ना
तो
क्लैश?
बी ई और एफ
Actually, sir, actually, if we talk to every student, then any slot can clash because every student has some class at a slot.
फिर भी
तभी तो वो
ट्राई कर रहे हैं।
स्लॉट्स ना, हाँ नहीं, वो प्रशांत, वो हमेशा वो चीज क्लैश होती है, ठीक है, वो काफी देर से करा रही है।
अच्छा
वो हमेशा जो वो चीज हमेशा क्लैश होती है, तभी होता है कि 1.5 आवर के कहीं पे बीच में मिल जाए स्लॉट्स। ठीक है।
तो
Sir, but
फ्राइडे का
एक
ही
बार
चांस
फिर
है
भी
फिर।
we can try asking, कभी कभी ऐसा, क्योंकि there are less students, तो ऐसा possible है that एक slot हो जो किसी का भी ना हो।
See, let's try for that Friday. I will talk to sir right now after the class in the evening. Okay, Friday की confirmation की वेट करते हूँ, मैं एक बार सर से बात करता हूँ, फिर भी अगर हुआ तो हम कुछ आगे सोचेंगे कि कैसे प्लान कर सकते हैं फॉरवर्ड में।
So if required, if it is feasible, then we can use half an hour of the lunch break on Monday. I mean,
सी हाफ एन आवर में ना टॉपिक कवर नहीं होगा, जैसे अभी आपने देखा होगा कि मेरे को जस्ट बेसिक्स ही बताने में, रिकैप करने में हाफ एन आवर लग गया था।
so it is half an hour in continuation with the normal class actually at D slot.
Yeah, that is one thing that can be tried. Let's see what happens there. there वो तो है ही हमारे पास एक सोल्यूशन, बट हाँ वो सब है मेरे माइंड में, वो मैं बस सर से डिस्कस करता हूँ फिर फाइनली, क्योंकि कोई प्रॉपर स्लॉट नहीं मिल पा रहा है। Okay, so let's table this topic for another time, right? So let's go to the task that we want to do. Acha, so how many of you know about convolutional neural networks? Okay, if you do not know about convolutional neural networks. Okay. Okay, fine. So we will cover convolutional neural networks in details the in sometime later on. Okay. So I will just work with the fully connected networks for now. Okay, so I'm just yeah. So the very first thing in Python when we start coding is we actually import the stuff that we're going to use. Okay. So in this case, we are going to use TensorFlow. So we are importing TensorFlow and then renaming it as TF. What is the benefit of doing that is that if I just write import TensorFlow, everywhere inside the code, when I want to use TensorFlow, I would actually have to write something like TensorFlow dot something. Okay, this is how I can use the functionalities of TensorFlow if I just use import TensorFlow. However, if I create it as TF, I can write TF dot something. Okay, so this is one. So that's why and even you can see that in this print statement, we are printing the TensorFlow version, and there's something is this function version function, and we are just writing TF. Then we are going to also import some specific things that we're going to use. In this case, I'm just going to import dense layer. That's it. I'm not going to use any other layer. Okay, so the dense layer is actually presenting TensorFlow.keras.layers. So from there, we can import all the layers that we want to import. Okay, and finally that we want to import a model because we want to create a TensorFlow model. So we want to import model. Now it's always important to know that these are all classes. This is completely object-oriented programming. TensorFlow is object-oriented programming. So what we are doing is TensorFlow is a class, and we are importing an object of that class. Similarly, dense is a class, and we are going to create an object of the class dense. Similarly, model is a class. So in Python, if you import anything, you are actually importing the complete class. You're importing the whole class with you. Okay, so we'll just run this part of code. Okay, so we are going to work on MNIST dataset, right? So here what we did is we actually created an object for the MNIST dataset. The MNIST dataset is available in TensorFlow itself in tf.keras.datasets.mnist. Okay, so we have loaded the MNIST dataset. I can show you some images of the MNIST dataset, how the MNIST dataset is there. So this is an example of the MNIST dataset. So MNIST dataset, each image is a 28 cross 28 image, where each image has a handwritten digit over it. These are binary images. Okay. One important property of an image is that is always you need to remember is that the pixel values in the images when you load any image is between 0 to 255. Okay, so that is the range of the pixel values of any image. So these are MNIST images. So these are 9 MNIST images. We can see that this image has a 4 written on it. So a task is that given this image, we need to tell whether which digit is handwritten over this image. So in this case, the ground root will be 4, 1, 0, 1, 1, 7, 8, 7, 2. And these are the corresponding ground roots. Okay. So this is our task that given this image, we need to identify that what is the digit written over these images. So these are the MNIST images. So we are just loading the data set from the TensorFlow itself. Okay. Now we are going to, so this is a class. Now MNIST is an object of the class. So if there is an object of a class, the object will actually have some functions that we can call. The class will have the function that we can call using this object. So the function that we are going to call, Prashant, can you mute your mic? Yeah. So the function that we're going to call in this class is load data. So what load data function will do is it will actually return us the data set of the MNIST, okay, in this format. So it will actually give me X-train and Y-train. Yeah, Dipali. Yeah, Prashant, you raise your hand. Okay, no issues. Okay, so whenever we work with any data set, so what we have training data and we have testing data. Our data is actually composed of input and ground truth. So a combination of input and ground truth is called a data point. Okay, so in this case, my X train is the input and my Y train is the ground truth. Similarly, my X test is the testing input and my Y test is the ground truth. So I can just load this. So it has downloaded a dataset and loaded it in X10 by train. I'm also going to import one aspect, that is import numpy as np. So numpy is a package that helps us with array management. Okay, so I'm going to import numpy as well. So the benefit is that now I can do print x10 dot shape. Yeah. So now what it did was, by importing the numpy, so the MNIST dataset that was loaded, it was loaded in numpy format. Okay, so these all are my numpy arrays. So now I can, for any numpy array, I can utilize the function dot shape for that array to get the shape of that array. Okay, so in this case, my X train, the shape of my X train is 60,028.28. What this means is that each image is 28,28, and I have 60,000 such images. Similarly, I can print my Y train dot shape. So my Y train was the ground truth. Now the ground truth is nothing but integer values corresponding to each image. What will be the integer values? That which class the image belongs to. So since ground truth is just one integer value per image, so I have 60,000 integer values. So this is just a numpy vector of just 60,000 values, and each value gives the class to which the corresponding 60,000 images belong to. Similarly, we can print the shape of test. You can ask me to zoom a bit. Okay, so now we can see that the access dot shape is 10,028,28. That is, I have each image is 28,28, and in testing data I have 10,000. And similarly, we can see my Y test. And you can see that for my labels of testing, that is my Y test, which is the labels of testing. Since the testing images were 10,000, I have 10,000 corresponding labels for testing. So I hope the data is clear. This thing is clear. What's X train, Y train, X test, Y test, because this is important. X test is my training images. Y train are my training labels. X test is my testing images. Y test is my testing label. Any issues till now? Okay, no issues. Another thing I want to say is, even everything in the Python is object oriented. So when I got Xtrain and Ytrain, they were also objects of the NumPy class. That's why I can call the functions from that object. So I can just name the object and call the function. So they were also objects of the NumPy class. Everything in Python is object oriented. Okay, so it's good that if you want to work with Python, brush up with your object oriented skills. The so can anybody tell me what are the basic object oriented aspects that we that gives it power, that are unique to object oriented programming? Anyone? There must be some CSC BTech guys.
So like abstraction,
Abstraction.
encapsulation, polymorphism,
Yeah.
and inheritance.
Inheritance. Yeah. Yeah. So these are four basic ones. We are actually going to utilize inheritance in this code. Okay, we are going to utilize inheritance in this code. Okay. Yeah. So we have loaded the data. Got it. And now what we are going to do is that we are actually going. Now it's important to note that whenever we talk about images, image of every pixel value in the image lies from 0 to 255. Okay. Now I'm going to give each of you a task that each of you have to go and see later on your work. Why we always need to normalize our inputs whenever we are working with neural networks. Okay. It's for each of you. If you know, then that's fine. If you don't know, please look into it. This is one of the most important aspect to normalize our inputs with a neural network. You can look into it on your own, that why we need to do it. It's a basic deep learning concept. So since we know about that the images are from 0 to 255, we want to normalize the images from 0 to 1. So to do that, the pixel values on xtrain were between 0 to 255. So to normalize it, we just divide the xtrain by 255 and we divide the x test by 255. So what does is that my xtrain and x test are now normalized. Okay. So I have now normalized my xtrain and x test. It's a simple bit of code, right? Now what I'm going to do is I'm going to flatten them. Okay. Now my x train. So the very first thing that I'm going to do is I'm going to convert wait, x train is equal to, so I need to flatten them. So for flatten we have np dot reshape function. Okay, so np dot reshape function will actually flatten the systems. So inside the reshape function, the first thing we are going to call is the array that needs to be flattened, and then to what size that array needs to be flattened. So whenever we flat, what we say, we are flattening each of the images, right? So if I'm talking about xtrain, so when I'm flattening xtrain, what I'm going to do is that I'm going to have, now each image was a 28 cross 28 matrix. Now I'm going to have a single vector for each image, but I will still have 60,000 vectors because every image is independent. So this was the array 60,000 comma 28 comma 28. I want to preserve the very first value of that array. So to preserve any value, I will just write -1. -1 will just preserve that axis when I'm flattening. Okay. Now I want to flatten this 28 comma 28. So now the next axis will just be what it will be, extend dot shape 1 into extend dot shape 2. Yeah. So now what I'm doing is, see this value, and so my image was extend.shape1, that was 28, and extend.shape2, that was 28. So whenever I write extend.shape, it provides me a tuple, and to access each and the individual values of the tuple, I can use the indexing. So this is the 0th value of the tuple, that is 10,000. This is the first value of the tuple, that is 28, and this is the second value of the tuple, that is 28. So now what I'm saying is, you preserve the very first aspect, the very first axis, but make the second axis as the multiplication of second and third axis. So now if I print,
Excuse me, sir.
yeah.
So I just wanted to ask one thing. When will the recording of this lecture be uploaded? So actually, I have a problem. I have to conduct a workshop at 4, and since I can't move that because उसके बाद भी मेरे को कुछ काम करने थे, so I'll actually have to leave now. So
Okay, we will record it as soon as possible.
Okay, sir.
Yeah.
And sir, like you won't be teaching anything about CNNs today, right?
No.
Okay, sir.
Okay. Okay. So now if we see the shape of xtrain, now my xtrain shape has become 60,000 comma 784. Okay, so Dipali, for that aspect, what I can say is that first let the class timings be finalized. They are not yet finalized. They are still temporary. Let them be finalized. Then I will ask editor to do that. Okay, so now where was I? Yeah. So my extrain, the initial shape of extrain was 60,000, 28, 28. But now we can see now my shape of extrain became 60,000, 784. That is, now I have 60,000 images and each image is a flattened image 784. I can do this thing for my testing data as well. So for that, sorry for that, test, 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 and test. And I can print the testing shape as well. Test. So now my testing data is also 10,000, 784. Okay. So now I have flattened my data to be so that it can work with my fully connected networks. Another thing that I'm going to do is extend is equal to extend dot as type float 32. So now why I'm doing this? So whenever we load images, images are actually loaded in unit 8 format. So, but all the neural networks, the TensorFlow, whenever we are going to use TensorFlow, the TensorFlow actually requires the input in a floating point 32 because all the operations that we perform are floating point operations. So we need to convert all the input to a floating point input. So we are going to convert our extrain to a floating point 32. Similarly, we are going to do the same for xtest as well. See, always remember to do these steps. So what was the first step? Always remember to normalize your data. So this is the very first step. Second step, always, sorry for that. Always remember to reshape your data correctly so that the neural network is ready for the data. That is second step. And finally, the third step is always remember to convert your data to a 32-bit floating point precision. Okay. These are the three steps which always needs to be done. Okay. So now we have normalized the data. Okay. So now what we are going to do is we are actually going to create my model. So a few of you are familiar with the sequential API, but we are not going to use the sequential API. We're actually going to use the model subclassing API here. So for that, what I said was that everything is a class. And the best part about class is that whenever we are loading any class, we can inherit a class. Okay, so by inheriting a class, I can actually get all the properties of that class, and then I can change some of the properties or create my own properties over that class. So what would happen is that I want to create a model, so I will inherit the class model. So I'm going to create a class. Okay, the class name can be, let's say, my model. So I'm creating a class my model. Okay, but this my model class needs to inherit the TensorFlow's model class. So I will write that this my model class inherits TensorFlow's model class. So I'm creating a class my model, which is inheriting my TensorFlow's model class. So now what's happening is that this my model has all the properties of the TensorFlow's model class. So all of the properties there. So now I'm going to create my own model for this. So whenever we create a class, what is the very first thing is do? We actually define the initializer. So I'm going to define an initializer and I'm going to pass self through this initializer. So for self means for that given, Wait, that's not correct. Yeah. Self means for that given object, you do this. So whenever I create a class, so this in the self, that same object is passed. So this is something in C++, we don't need to write self, but here we need to write self to define that we are doing this for the current object itself. So now I want to initialize my own class. So before that, I'm going to initialize the model class, the actual class that is there. Okay. So what I'm going to call is, so this model class, this is the parent class of my model class. Okay. So if inside my model class, the class that I'm creating, inheriting the parent class, if I want to call the parent class, the function for that is super. So if I write super and I write my model, comma, self. So what it's doing is, it's now I'm calling the super class of my model. That is the model TensorFlow's model class itself. And but I'm also telling the model class to call it with respect to the current object. Okay. And then I'm calling its initializer. So what I'm doing is, in the lieu of the current object, that is a self object, call the super class is initializer. So first thing is that if I want to initialize my model, I first need to initialize the super class so that I can get all the variables of the super class to work with. Okay. So this is something about object-oriented programming. If you must practice how to use object-oriented programming in Python, how to use inheritance in Python. Now the thing is that we actually want to create a dense layer. Okay, that is my first hidden layer. I want to create my first hidden layer. To create my first hidden layer, I will write self dot hidden one. Okay, so now I'm actually creating my first hidden layer there. So this will be my dense layer. That is a fully connected layer. Okay, so as you can see, we had imported a dense layer from the layers. So I'm calling the function dense. Okay, and I'm giving, let's say, 500 neurons, and I'm saying that activation is equal to, let's say, ReLU. Okay, so now I've created my first hidden layer. So what I'm doing is, again, whenever I call this dense function, so this dense, it's important to note that this dense is a TensorFlow's inbuilt dense function. So what it's going to do is, it's actually going to initialize a layer for me having 500 neurons and 500 biases. So I've initialized the layer having 500 neurons and 500 biases. Okay. Okay, so this is what the dense is doing. It's initializing that layer as hidden one. Then I can call, I can create a second layer that is hidden two. I can again call the dense function. This time I can say, let's say 100 neurons. And finally, I can create my output layer, which will again be a dense layer. Okay, but it won't have any activation. 10 neurons, it won't have any activation. So now the initial layer was already defined by the 784, so I don't need to define it. Okay, the very first thing I need to define is my first hidden layer, 500 neurons. I've with activation ReLU. I've defined my second hidden layer, 100 neurons with activation ReLU, and I've defined my output layer with 10 neurons because I have 10 classes. So now I have initialized my model. So the model contains 3 layers, and I have initialized my model. Okay. Any doubts?
Sir, hello, sir. Can you hear
Yeah,
me?
yes, Utkarsh.
Sir, in the case means in the case of dense, can the layer be two-dimensional?
No.
No, means dense function does not require only one length of the layer.
Yeah, because they're fully connected layer, just a number of neurons.
It means dense is a fully connected layer. Means
Yeah,
if
dense is
dense
a
is
fully connected layer.
okay.
Okay. So this is a fully connected layer. So I'm calling a fully connected layer with 500 neurons. I'm calling a fully connected layer with 100 neurons. So basically fully connected or densely connected.
Okay, sir.
Okay. Okay. So now once I have done this, once I have initialized it, so now I can override some of the functionalities of the model class itself. So model class has a lot of functionalities which I can override. So one of the functionalities is how the forward pass happens. So whenever you are creating a model, how the forward pass happens. For that, inside the model class, there is already a function called call. So there's a function called call. Sorry for that. Def call. Now the point is that by using inheritance, I can override the function call. So that if I call this mod class, if I call the class my model, this function will be used. My own call function will be used, not the call function given in the model class. Okay. So this is overriding. So we can override the functions of the previous class. And this call function will actually tell me that how my input goes through the layers and gets me the output. So whenever we create a function, the first thing that we write is the self. That is, we are creating this function for the current object itself. And also we just giving one argument that will be the input. Now X will be my input. Okay. So now what I'm going to do is I'm going to do X dot self dot hidden one, and I'm passing X. So now what I'm doing is hidden one was a dense layer. X was my input. I'm passing my input to my first dense layer. So now I can just write it, which is H1. So H1 is the output after passing through my first dense layer. Then I can pass H1 through my hidden 2 to get my H2. So this was my input. It was first passed through hidden 1 to get H1. Then I passed H1 through hidden 2 to get H2. And then final my output, or basically what we call this as logits. That's a better word for that. Okay. Logits is equal to self dot output H2. So now I've got the logits by passing it through the output layer, and I'm going to return the logits. So now this way I've created my model. So inside my model, I have inherited all the properties of the original model class, whereas I have just changed two properties, the initializer and the call. First thing, while changing the initializer, I called the supers initializer first and then created the variables that I want, that is created the layers that I want. And in the call function, I told my model that how these layers will actually work over the input. So given an input, the model will apply first hidden layer, then the model will apply second hidden layer, and finally the model will apply my final output layer. Okay. See, the best part about making the model like this is that you can create any arbitrary models. You're not restricted. You can create models with TensorFlow functionalities in between. You can just utilize any TensorFlow functionalities. You need not utilize any layers here, and those functionalities will be in part of the model. Anything that has TF dot in it, you can utilize in the call, or anything that you want to initialize that has TF dot in it, you can initialize and utilize. Oh, sorry for that. Utilize here. Here you are completely free. You are not just restricted to layers. You are not just restricted to a sequential model. You can work with the hidden layers any way you want. So for example, so in hidden one I can pass X. Even in hidden 2 I can also pass X. So now what's happening, I'm creating a 2-branch model. So where X is passed through 2 different branches. So this is a 2-stream model. I can create a 2-stream model. I can create an N-stream model. I can do anything that I want whenever we are working with the subclassing. So that's why always make a practice of creating models this way. Okay. So we're just going to run this code. Okay, so now I'm going to call this class. Wait, output likely because it conflicts. Okay, so don't use output, use output layer. So the error was because output is one of the keywords in TensorFlow, so never to use output. So use an output layer. So that's a better variable name. Yeah. So now we can see that now my model, this model with small m is my own created model, which follows the properties that were derived by this class, and which also follows the properties of the TensorFlow's model class as well, because that is what we inherited. Now I'm going to create the loss object. Okay, that is my loss function. So the loss function, I'm going to use the categorical cross entropy loss function. I'm going to use a sparse categorical cross entropy loss function. So what it does is that, first of all, I'm calling from tf.keras.losses. How is there anyone who does not know what a categorical cross entropy loss function is?
So I know about normal basic cross entropy loss. I don't know what categorical signifies actually.
Okay, so basic cross entropy loss, how do you give your ground truth?
It is a vector of 1 and 0, basically
One hot encoding,
one
right?
hot. Yes.
Yeah, another word for one hot encoding is categorical format. So the cross entropy loss, you know, that's categorical cross entropy loss.
Okay, so got it.
Okay, so the categorical cross entropy loss is nothing the cross entropy loss in which from the 10 outputs of the model, we apply the softmax activation, and the ground truth is also a vector of 10, which is one hot encoding format, and we compute the cross entropy between the output probability and the required one hot encoding, that is the categorical ground. But the point is, if we create, so to work with categorical cross entropy loss, we need to redesign our labels. Now the labels cannot be integer, they not be one hot encoding vector, which is not always practical, because we are always not working with 10 classes, 20 classes. Sometimes we're working with 1,000 classes, 10,000, even a lakh of classes. So if we convert each label to one hot encoding labels, so in one hot encoding, what happens is the size of vector is equal to the number of classes. And if let's say you're working with 10,000 classes, this matrix, your label matrix will become so huge that is you won't be able to fit inside your memory. So we actually never convert our labels to categorical. We always keep our labels in integer format itself. So to tell the TensorFlow that I'm going to use the categorical cross entropy loss, but my labels are actually coming in integer format. You need to convert them to one hot encoding format. I will use the sparse categorical cross entropy loss. So when I use the sparse categorical cross entropy loss, this word sparse actually tells the TensorFlow that yes, I want to convert the integers to one hot encoding format. However, I'm not doing that myself. You yourself do that. So the TensorFlow in between automatically will convert my integer values to one hot encoding formats. Another thing that I want to specify is that when I was calling the loss function, I provided this argument from logits equal to true. So you can remember that I actually wrote my output as logits. So how we define logits? And it's not a theoretical definition. It's not, but it's more like a practical good sense definition that everybody should use the word logic whenever creating a code. So the meaning of logics is that the output after the final layer, but before the final activation. So in classification networks, what is the final activation that we use? Gehan.
Softmax active.
Softmax activation, right? But here you can see that I have not applied that activation.
Yes,
Since
sir.
I have not applied that activation, I'm going So these are my logics. This is not output of the model, but this is the logics of the model. So now here I'm telling TensorFlow that the output is from logics. It's not from activated output, it's from logics. So if I write this from logic equal to true, then the TensorFlow will know that it needs to apply the activation function as well. Okay.
Sir,
See there, yeah, Utkarsh?
sir, so losses means losses does know what activation function it should apply.
Yeah, loss knows.
So means so softmax will be applied or
Yeah,
any
it will
other
be
function.
softmax will be applied.
Okay, sir.
Yeah. So the activation function that will be applied is fixed with respect to the loss function that you are calling. Okay, so now what we have done is, now we have created a loss object. So this object, whenever I call this object, I will provide it two values, the ground truth and the output of the network, and it will compute the loss given all the properties that I have defined. So it will compute the loss, it will compute the cross entropy loss, given that the ground truth is actually coming in integer format, and it needs to also apply the activation as well. So now I've created a loss object, and whenever I need to compute my loss, I can call this loss object. Okay, so I've created a loss object which will compute the loss for the ground truth and predicted value given all of these properties. Similarly, I'm also going to create an optimizer object as well. That is my optimizer. And I'm going to call tf.keras.optimizers. I'm just calling the Adam optimizer. That's it. Okay. Now, another thing that I'm going to do is that, so these are just some stuff I'm going to copy paste. I'm not going to type. I will just explain it. So now I'm just creating the metrics. Okay, so this was the loss object was for training the model. Okay, I'm also creating some metrics as well. Uh, as well. So what I'm creating is that my train loss is just a mean metric. I will show you. Actually, I will come to the metrics later on. I will show you how they are used. Okay, I will come to this part of the code later. Can anybody tell me what this line is? What does this at the rate means? Anyone?
Can you repeat the question, sir? I didn't understand.
Say this line I have written. The very first thing is at the rate. What does this at the rate means?
So is it some annotation to do some pre-process?
Of course, everything is an annotation to do something in programming.
Yes.
So what is something that at the rate does?
So like we have to create the computational graph. So every time we don't want to call this to make a computational graph and then the stuff which we want. So we are creating
So
this function.
that's df dot function. I'm not talking about. I'm just talking about at the rate, right?
So it's a decorator.
It's a decorator. Yes. And what does a decorator does?
So it takes on a function and does some processing over it and returns another function.
Yeah. Okay. What is the meaning of that? In just layman terms, how can we? Let's forget about this for now. We will come to it later on. Okay. But just remember in back of your head that there's something called a decorator, and its property is to take a function as an argument and return another function. Okay. So now let's create the function that we want to use, which we will be decorating it. The function that we will be decorating. So the function that we are going to use is I'm going to define my training step. So the training step will actually get two inputs, images and labels. Okay. Now I'm going to define my training step. How the training step was defined: forward pass, loss computation, optimization, right? Okay, so let's do that. That's my forward pass. So what I'm saying is that, wait, did I call training? Sorry for that. Model images. Another thing that I want to call here is training is equal to clue. Okay, just a variable we usually use. We are not going to use here, but this is important when we are working with something like dropouts and batch normalizations. I will show you one example in the next class of when we need to use this training, but it's important to keep it in call. Okay, so I'm calling that training. So what I'm doing is I'm taking the images and passing them through the model to create my predictions. That is the forward pass. But another aspect that I want to tell is that while I'm doing this forward pass, I also need to compute the derivatives as well. Okay, since this forward pass is a pass for training, so I need to compute the derivatives as well. So to tell the TensorFlow that I'm going to compute the derivatives for all the system that I'm writing later on, what I need to do is I need to call a gradient tape. So what gradient tape does is, so it actually parses through all the codes that I've written within the scope of gradient tape and keeps on computing their gradients and putting them in this variable tape. So whatever, if I use a model, if I use a variable, whatever thing I'm using here, if it contains trainable variables or if it contains any variables, and if it's inside the scope of my gradient tape, what it will do is that it will automatically keep on computing the gradients and writing those gradients inside the tape. That is the subgradients at each layer. It will compute the subgradients at each variable, that is at each parameter, and keep on writing for each parameter the subgradients in the parameter tape. Okay. So once I have so now I'm telling the model that now you need to start computing the gradients. Okay. So when does the model need to start computing gradients is, first of all thing is I will define my forward pass where I will pass my images to the model to get predictions. I might have to run it again. Yeah. Okay. Through the predictions. I will have to, and now I've got the predictions. Now these are my logics. Now, and what I need to do is I need to compute the loss. So the loss is equal to loss object between labels and predictions. So labels was the ground truth. So I'm saying that loss object was the object which has the properties of computing losses as we had defined. And we are now doing labels and predictions from the ground truth. Okay. So now this is the forward pass complete. And since this complete forward pass, that is from images to loss computation, is within the scope of gradient tape, this tape, all the gradients have been actually recorded in this tape. So now what I want to do is I want to now what I want to do is all the gradients that were recorded were the subgradients of each variable. Now I'm going to tell the TensorFlow that for each of the variable you have recorded the subgradients, but what is the actual gradient that you need to compute? So what is the gradient that you need to compute? You need to compute the gradient of loss with respect to all the trainable variables of the model. So you have the tape which contains all the subgradients that you need. So from that tape, you need to compute gradient of the loss with respect to all the model's trainable parameters. So now those gradients are computed, which will help us in minimizing this loss function. Okay. And then finally, I'm going to apply these gradients. So what I'm doing is I'm applying the gradients. Okay. So I'm calling my optimizer and telling it to apply the gradients. So what gradients it need to apply? It needs to apply the gradients which it computed over the trainable variables using this optimizer that I defined. So it needs to apply gradients, which gradients, the gradients that I computed, that is of loss with respect to trainable variables, to the trainable variables using the optimizer that I called initially. So that is how I'm telling the optimizer to apply. And this is where my gradient update is happening. So this updates my gradient. Okay. Yeah, so this updates my gradient. And finally, my train loss and I think I missed something. No, wait, I think I missed something. Not sure. I'm seriously missing something very drastic in this code. I'm not sure.
In the train step, we are not using my model class, we are using the model.
Yeah, because see, we created an object model of my model.
Okay.
So just to rename CS672. CS6. You can create any name you want, but just to make sure that everywhere it's that name itself. Got it. Everywhere is the same name itself. You can use any name that you want. Doesn't matter. But I'm going to use model also only because it's
Sir,
yeah.
so gradient should be in the loop now, means with the TF without gradient tape as tape.
No. See, we need to compute the gradients of loss with respect to the parameters, right?
Yeah.
The trainable. So the trainable parameter should be inside the scope of gradient tape.
Okay.
So for any variable for which you need to compute the gradients, those should be inside the scope of gradient tape. Because
So means prediction and loss are in tape. Yeah.
Yeah.
Okay.
Beware, TensorFlow and Pytorch, they drastically fail on double derivatives. Okay, always keep your gradients away from the scope. They do not work well with double derivatives because they're just one point that I want to add, because they never compute the actual derivative. Okay, so what they do is they actually compute approximate derivative. Okay.
So where is this term tape coming from? Like in line 3, 4, we can see that the tape will come from line 2, but in line 5, where will that tape come from?
Yeah, so basically tape is now the variable that I'm using for TF dot gradient tape.
Yeah, in that
Okay.
context, in 3 and in 3rd and 4th line only, right?
No. See, first look at line 2.
Yeah.
Okay, let's first look at line 2. So what I'm doing is I want to create a gradient tape. So I will give it a variable name tape.
Yes, sir.
So now I have created a variable tape, which is nothing but instance of TF dot gradient tape.
Yes, sir.
So whatever I wrote in this scope of this tape, the tape will record all the subgradients. of this scope.
But the tape variable itself is inside that context, right?
Inside what context?
With tf.gradient tape as tape.
Yeah.
If that context ends, will that variable
No,
still be in the global
it will
context?
still be. It's in the context of train step.
Okay.
Okay, it's in the context of train step.
Okay.
Yeah. Okay. Okay. Yeah. That's why I skipped this part. The main. Okay. So now the loss that is actually computed is actually computed. So we actually input images in a batch phase. Okay. The loss that is computed for each value of the batch. So now the very first thing is we need to actually take the average of the loss so that we can print the loss. So for taking the average, we are using a mean function. Okay. The mean function, we are calling an instance of the mean function as train loss, and then we are applying the train loss over loss. That is, you take the average of this loss that we are having. Similarly, we are going to use the metric as sparse categorical accuracy, which actually computes the accuracy based on sparse categorical loss function. Okay, it knows the loss function that is being used is a sparse categorical loss function. So we are going to use the metric as sparse categorical accuracy, and I'm going to pre-predict my accuracy between my labels and the predictions. So what it will do is it automatically notes that these labels and predictions are in coherence with the sparse categorical loss function. So it automatically knows how to predict their accuracy, that whether these labels and predictions, they are saying the same class or not. Okay, so this is my train step. Now the point is, when I will call this train step, what would happen is that it will run this whole system. It will run this whole system line by line as it does in Python. So Python is interpreted language. So inside interpreted language, what happens is that the whole code is ran line by line. It's not like C or C++ where the whole system is pre-compiled and it just ran once using the machine language. That never happens. There's no pre-compiled version of the system. In Python, everything is ran line by line. Okay. So that is the problem. So when everything is done line by line, things are actually very, very slow. But we know that the properties that we have defined in this train step are going to be run a lot of times because we are going to have a lot of batches. So this train step will work from one batch. We are going to have a lot of batches and we are going to run for a lot of epochs. So we know that this part of the code is actually going to run a lot of time. This function is going to run a lot of time, that we cannot have it that it runs line by line. So that's why we are going to decorate this function. So what it means is I'm going to give this function as an input to some other function, which is going to return me this function again. So now let me write my decorator line. So now what it does is it decorates the function train step such that now the function train step is given as the argument to tf.function, and tf.function has now returned a new train step. The property of that new train step is defined what happens in tf.function. Okay, what? So this is a decorator. This function can be any function. It's not necessary tf.function. Okay. Okay, there can be a lot of other decorators. So what a decorator does is that it takes this function which we have defined, train step, it passes this function through the decorator function and then returns a new function, train step, such that whatever the properties we defined in this decorator function, they are embedded in this train step. So in the case, so that is a decorator. In the case of tf.function decorator, what it does is when it yeah, Utkarsh?
Sir, this means that it is passing a class function to a class now, like that.
See, TF dot, see, I'm actually simplifying what a decorator does very much.
Okay.
Internally, what's happening is complex. I'm actually simplifying it a lot. If you want to
Okay,
look
sir.
internally what's happening, it's up to you, but I'm just trying to simplify it, that it decorates this function. That's it. Using the
Okay, sir.
properties of the above function. That's what I'm saying. Okay.
Okay, sir.
What is the property? That now this function will become a computational graph. That is, TensorFlow will actually compile this function. And whenever I will call the train step, this function will never be called. The TensorFlow's compiled function will always be called. So by decorating it as TF dot function, what I'm doing is, whenever the first time this train step will be called, it will compile this function. It will create its computational graph. And every time when this function is called, these such of codes will never be used. What is going to be used is the compiled function. And because of that, this whole system becomes very, very fast. The aspect of computational graph comes in. So whenever you create a function for training, always decorate it with TensorFlow.function. Or whenever you create a function inside your code, which is going to be used a lot of times, you always decorate it as tf.function, so that TensorFlow pre-compiles that function, creates a computational graph, so that that function can be used again and again.
So this is model.compile.
No, this is everything basically.
Okay, sir. Model.fit and model.compile, both.
Sort of like, I mean, see, we are doing everything ourselves here.
Yeah. Okay, sir.
So there's no model.compile, there's no model.fit now.
Okay, sir.
Okay. So that's done. So now I'm not going to go into details of I have created my testing code initially itself. I'm just going to copy paste it. Oops. Copy, I hate copy pasting. Yeah. Why it's saying error? Oh, no, it's fine. So now in the test step, okay. So now I'm going to write the test step as well. Now in test step, since we do not need any training, we do not need any gradient, so we are not going to use the scope of gradient tape. So in test step, everything will happen without the scope of gradient tape. So again, we are passing the images to the model. We are again computing my testing loss. And then we are again taking the average of the test loss, and we are again computing my test accuracy similarly. But since we are not going to train during testing, we are not going to create any gradient tape in this case. And again, since testing is going to be done a lot of times, we are creating a TensorFlow decorator. We are decorating it as a TensorFlow function. Okay.
One question, sir.
Yeah.
In that optimizer dot apply gradient you have written,
Yeah.
so it seems like you have given everything to a function, but it does not seem to be like. I mean, does the sequence actually matter over there? Like if I'm searching the line sequences.
Aditya, can you repeat that?
I was just saying that it seems like you are providing uh, arguments to a function, like
Hmm?
you have to do this, you have to do this, but you have not specified any sequence. So what I was asking was like if we interchange the sixth and seventh line in that cell, So does it matter actually? Because you are actually creating a computational graph, right? So
It will matter. See, it will matter because before applying gradients, we need to
okay,
compute the gradients.
gradient. We need the gradients. Okay.
We need the gradients.
Okay.
So the computational graph will follow the same sequence.
Yeah, it seemed like we are actually you provided the optimizer in the end actually, and did the backward propagation earlier. That's why I asked. It is actually just compiling, right?
Yeah. So basically, here we are just computing the gradients. Here we are actually doing, see, that's the point. In theory, we say that we do a forward pass, we compute the loss, and then we do a backward pass. But things are actually happening in parallel. While doing the forward pass, I'm also computing my subgradients while doing the forward pass. And then once I have the subgradients, here now I'm applying the chain rule to compute all the gradients. And once the chain rule is applied, and what is chain rule? Chain rule is just a multiplication operation. So here it's just multiplying, it's just applying multiplication operation. And here once we have computed all the gradients with respect to the chain rule, we are applying those gradients. So everything is happening on parallel. At every layer, everything is happening on parallel.
Okay.
Because we are using gradient tape, because while we are doing the forward pass, we are computing the gradients as well.
Yes, I got it.
So now what I'm going to do is that I'm actually going to utilize to manage the data. Okay, we never use NumPy arrays. Wait, let me just. Yeah, this is what I was missing basically, and then create a data. Okay. So, okay, so what it does is that, so now I'm going to use a function. So I'm going to create an object of tf.data. Okay, I'm going to create an object of tf.data. The good thing about creating objects of tf.data is that it automatically inherits the properties of TensorFlow. The data is automatically created in such a way that it inherits the property of the TensorFlow. Okay, so there are many different ways to create data set, but if you have NumPy arrays, you can use either this function tf.data.dataset from tensor slices. Okay, this is one of the function that you can use for NumPy arrays. There's another function. Let me just search that function. Okay, no, this is the only one function. Never mind, that's for something else. Okay, so now what I'm doing is, so I'm telling to it to create a trained data set. Okay, such a data set which has the properties of TensorFlow. So for that, I want to create a trained data set which has property of TensorFlow. So for that, I need to tell my TensorFlows that from where the data is coming. Okay, so the data is coming from tensor slices. So this is a function which we can see creates a data set whose elements are slices of the given tensors. So what I mean by slices is that whatever data set that I'm providing here, it will slice the data set into smaller chunks. Okay, so this data set contains 60,000 images and 60,000 labels. Now I cannot process 60,000 images and 60,000 label at once. I need to break this data set into some chunks. So that's why I'm using the function from tensor slices that this is the full data set, but you need to break this data set into chunks. And each time you will only going to work with one chunk. Okay. Then I'm providing some properties to it. That what should be the properties of this data set? The first property is that it should shuffle this data set, because whenever we initially load the data set, it's loaded in a very systematic format, that all the first class images are initially, all the second class images are initially, all the third class images are then, and so on. Okay, so we need to shuffle this data set. This value inside the shuffle is the buffer that we are going to use for shuffling. That is how much the shuffling should be in place and out place. So this value is how much we can use the in place memory for out place memory for shuffling, extra memory for shuffling. Okay, that is the buffer for shuffling. So the larger the buffer, the faster the shuffling will happen, but it will always also take more and more memory constraint with you. So, and then I need to define that how big each slice will be. So I'm saying that the slice will be in terms of batches, and the batch size is going to be 32. Okay, so now I've created this train data set, which I have told TensorFlow that you're going to use these X train and Y trains. You shuffle them and you slice them in batches of 32. Then I'm creating again my testing data set. Again, I'm telling TensorFlow that to take the X test and Y test. But since it's the testing data, I need not to shuffle. I just need to slice it in the batch size of 32. Okay, so this will actually create my wait a sec. I need to just run everything from starting again. Yeah, okay. So now I've created, now my data set is ready to be fed to TensorFlow. Now TensorFlow will convert this data set to the properties that it requires. Okay. So now I'm going to train my whole system. So the first thing is I'm going to define the number of epochs. Okay. So for epoch in range, I hope everybody knows this. Epochs. Sorry for that. Epochs. Okay. So whenever a new epoch starts, I actually created some metrics, right? So for training, I created train loss as a metric. So this was a metric. I created train accuracy as a metric. For testing also, I created two metrics, test loss and test accuracy. So the first thing is that I want to reset each of the metrics. So whenever epoch starts, it has to reset each of the metrics for that epoch. So I have reset the state for my train loss. Okay. Then I'm going to reset my test loss. Then I'm going to reset my train accuracy. And then I'm going to reset my test accuracy. So I've resetted all of my metrics. So that's why it's important to know why we are creating specialized objects. Whenever we create specialized objects, we can utilize that classes property. So whenever I create a loss object, I use tf.losses. I use a specialized object from tf.losses so that I can utilize all the properties of TensorFlow loss. Whenever I create an optimizer, I use tf.keras.optimizer so that I can utilize all the properties of optimizers. That is the function called apply gradients. And that's why when I created train loss and train accuracy, I created them from metrics. So tf.keras.metrics actually provide me a lot of functions that can be utilized as a metric. And one of those is that I can reset the metrics. I can do a lot of things with the metrics. Okay. Now what I'm going to do is I'm going to extract my training data set. Now my training data set, since was already divided into slices, so by using this, I'm taking the first slice of images and labels. And then the next time I will take the second slice, next time I will take the third slice, and so on. And I'm calling my train step. So my training data set, I broke down the training data set into slices, and for each slice, my train step will be called. Similarly, for my testing data set, I have again broken down my testing data set into slices of batch size 32. And for each slice, my testing data, what I'm going to do is I'm call my test step. So I'm going to call my test step, that is test images, comma, test labels. Now I've called. So now what will happen is, so when an epoch will start, it will reset all my metrics. Then it will start training. So this epoch will train my whole model, and then I will get new metrics. Okay. Then once the model has been trained on training data, I will test my model on testing data, and I will also get my testing metrics as well, because all of this has been defined inside my train step and test step as a metric. Finally, I'm going to print everything. What I'm going to print the epoch number. I'm going to print the training loss. Again, the another property of any metric is that I can use the value dot result to get the value. I'm going to print the accuracy. That is my train accuracy dot result, test accuracy dot result, and test loss dot result, and test accuracy dot result. So let's just call this function. Yeah, so epoch 1 is compute, where training loss was this, accuracy is this, testing loss is this, test accuracy is this. The epoch T2 is completed with my loss this, accuracy this, test loss, test accuracy, and epoch 3, and you can see that it's now computing all of the data reports. So this is how we actually write the what's happening inside. Whenever we use TensorFlow or sequential, compile, fit, we are not knowing that what's actually inside. What are the inside parameters that are there? However, here we can see that we have opened everything from inside. Everything is there. We now know that why there are 4 values, we can actually create these 4 metrics inside our own function. We need not to rely on fit. We need not to rely on compile. We can create our own loss functions. We can create our own training and testing step. And so these are the things that we can do. The reason why I said this was because in this advanced deep learning, majority of the codes that we will see will be such a way that we cannot create them by using just the sequential API. We need this kind of API to create those codes. That's why I opened this system for you, for just a simple tensor this data set. So any doubts?
So the sequential API actually does not do parallel processing, and the one you showed us, and one
Aditya, your voice is very much breaking.
So I was asking that the sequential API and the one you showed us, model classing API. So this is the difference between them. That sequential API does not do parallel, does the parallelization of the
See, what I did was I currently created a code that could be have written with sequential API by using this. But now you can see, you can write this part any way you want. Okay, you can write this part any way you want. You can create any metrics that you want. You can create your own loopings any way you want. You want to create test steps between train steps any way you want. Everything now is under your control. Currently, I just wrote everything the way happens in sequential, but you can see since everything was written by me, the way it happens in sequential API, you can definitely change anything that's happening inside.
yes.
Okay, so any more doubts? Okay, so that's it for today. And I think next week we will talk about CNNs and we will see two things. That first of all, we will see more about this data set part. That currently I just use the MNIST from the TensorFlow itself, but that won't be happening every time. That won't be happening anytime for us. We always have data sets stored in our own hard disk. So how can I load my own hard disk data set using tf.data? So we will see more about tf.data in details in the next class. And then we will also see how we can create some convolutional models as well. So that is to next week. So next week I will talk a bit about convolutional networks. Then I will show you that how you can load your own data set. So we will go into tf.data in more details. Right now we were just using numpy arrays, but there we'll be actually using actual images. So we'll go into tf.data for more details, and rest all of these things will be same. We just will use convolutional layers here as well. So rest everything will pretty much remain same. Okay, so one time I want to ask, so what was better? I mean, say a lot of time was wasted by doing this. We actually spent 2 hours on a lecture that should have been there in one and like worst case 1.5 hour or even 1 hour 15 minutes. But I actually not typed, but at least went line by line and putting that line inside the code at that moment. Was that better, or I can just have this whole code pre-ready and then I can explain it line by line? Which is better for you guys?
Sir, I think this is the right, I think.
Others?